Okay, hi everyone, and welcome to today's desktop seminar from the Royal Society of Chemistry. I'm Geraldine, I'm the Deputy Editor for our materials journals, and I'll be hosting today. So this webinar series showcases leading research on topics across the chemical sciences, and today we're going to hear from two excellent speakers focusing on topics in wearable sensing. So we have Professor Nanshu Liu at the University of Texas, Austin, and Professor John Rogers from Northwestern University joining us. So welcome to you. We have an hour today, so each presenter is going to be giving a 25-minute presentation, followed by an interactive question and answer session. So very brief note on housekeeping and etiquette. So we are recording this webinar. Attendees are all on mute, and if you have any questions for our speakers today, please just pop them into the questions box, and then I'll ask them to our speakers during the dedicated question and answer session at the end of each talk. Of course, we want everyone to enjoy the session and feel able to contribute, so please do be mindful of the agreement on the slide that we'll ask all our participants to follow today. So before we start, I'd just like to take a moment to highlight that the RSC has a variety of journals publishing research on wearable sensors. That includes our Horizons journals. So these are our premier journals for nanoscience and materials science, respectively. The journals have a real focus on new concepts or new ways of thinking, as well as truly breakthrough developments. We also have our latest theme collection actually on this topic on soft wearable sensors, and it's guest edited by a fantastic team of guest editors, and that includes our speakers today, John Rogers and Nanshu Liu. So we're very excited to have them with us today. You can read the articles published so far on the QR code on the slide, and there's more to come through peer review as well, so keep an eye out for those. Okay, so without further ado, I'd like to introduce our first speaker, Professor Nanshu Liu. Professor Liu is the Carol Cockrell Curran Chair in Engineering at UT Austin. Her research concerns the mechanics, materials, manufacture, and integration of soft electronics. She's a Clarivate highly cited researcher, a fellow of the American Society of Mechanical Engineers and the American Institute for Medical and Biological Engineering, and her talk today will discuss an e-tattoo body sensor network for human performance assessment. So I'm very excited to hear about your research, Professor Liu.
Thanks, Samantha. And let me share my screen. Do you see my screen and my cursor? Okay. First of all, it is a great honor for me to join Professor John Rogers in this RSC desktop seminar to talk about wearable sensors. Given the limited time, today we're going to give a very quick overview of many different types of e-tattoos that are developed at UT over the past few years. We would like to focus on human performance because it is a very comprehensive and interconnected system of our human body. When we talk about, for example, tactile athletic domain performance, it also can expand to other domains. We have to consider not just physical capabilities, but also cognitive capabilities like emotion, spiritual, and also health, especially cardiovascular health and neuromusculoskeletal health, as well as actually a lot of those kind of teaming tactical capabilities that it takes a long time for human to acquire, to practice and gain those capabilities. So as an interconnected human body, we know that it is essentially can be treated as a soft machine with a lot of distributed multimodal personal data from head to toe about our health status, intentions, and emotions. If we can have a reliable ambulatory sensing capability without being invasive, then ultimately the goal is to build even a digital twin of the human body in the cyberspace, such that all those real-time data can be updated to the digital twin for real-time personalized healthcare or performance and training, or even XR and metaverse. However, if we look into conventional wearable electronics, they are very Mm, rigid and bulky because of their silicon wafer-based electronics, and they have only a limited wearability, like you have to hang in front of the chest or just a strap on your wrist or finger. And we know that given those distributed signals across the body, we want better wearability and multi-site wearability. So therefore, we would like to promote the idea of a temporary tattoo-like wearables that are skin soft, hair thin, ideally could be worn anywhere on the skin, and provide a multimodal high fidelity sensing. However, anywhere is discolored because you must question how about the hairy scalp, and we are going to offer a potential solution for hairy sites as well. As early as 2011, when I was still a postdoc with Professor John Rogers, we pioneered the first epidermal electronics. Now I call them electronic tattoos, just to differentiate from electronic skins worn by robotic fingers, for example. So those e-tattoos feature completely inorganic electronic materials like silicon, metal, 3-5 semiconductors, but we pattern them into so-called filamentary serpentine, those kind of meandering snake shape wavy patterns, such that they can achieve as low modulus as our skin and as high stretchability as our skin. So after 14 years of development, now e-tattoo is a big field thanks to actually many attendees in the audience. People are really pushing forward the frontier of different properties of those e-tattoos in addition to being soft, thin, conformable. How about imperceptible, breathable, self-adhesive, self-healing, living, even incorporating cells, and so on. In terms of materials, although we focused on inorganic electronics, we also pushed forward for I'm going to talk about conductive polymer and some 2D materials, and a lot of other groups are pioneering liquid metal, silver, carbon materials, and so on. In terms of applications, we originally demonstrated just electrophysiological sensing and some solar cell or wireless antenna for energy harvesting. And then now it is also for like chemical sensing for a lot of variety types of energy harvesting, display, as well as drug delivery and stimulation. So today you are going to hear about those pioneering applications also from Professor John Rogers. So to differentiate e-tattoos from conventional wearables, we would like to highlight this microscale conformability to the microscopically rough skin surface. This is actually Professor Rogers' experiments showing that the thinner the film, even with just the van der Waals adhesion, no added adhesion, the e-tattoo can fully conform to the microscopic roughness of the skin. And we pioneered the first graphene e-tattoo that is so thin and also transparent that is almost invisible to other people. And the Professor Somaya pioneered the first ultra thin gold nanomesh skin conformable electronics. And this kind of conformability offers low contact impedance, which gives us high fidelity electrophysiological sensing. And if you are doing also mechanical strain or vibration measurement or some heat or sweat measurement, it can also give you the best transfer across the skin electronics interface. And when skin dynamically moves, there will be no delamination or slippage, which can minimize the motion artifacts such as tribal electric charges and give you accurate mechanical measurement. And they are not going to affect human motion or touch sensation if they are so thin and so conformable to the skin. And they are not going to be obstructive to clothes or other wearable gadgets like a VR headset or exoskeleton and so on. And you can even make them transparent and optically invisible to reduce social stigma. So here is just a video showing our first graphene e-tattoo that is manufactured on a conventional tattoo transfer paper. And by smearing some water, we are able to directly transfer the graphene e-tattoo on human skin with the graphene side touching the skin. And this is again under optical microscope. You can see the transparency and the conformability on skin. Because of the invisibility, we can put it anywhere, even on our face, without scaring away our friends. And around the eyes, we can measure a specific electrophysiological signal called electrooculogram (EOG), which is capturing the eyeball rotation-induced surface potential. Like when your eyes move left to right, the electrodes to the left and the right corner of our eyes can measure the horizontal eyeball movement. And this is a very sharp step function with a relatively large amplitude, like a millivolt level. So this is not muscle, this is not a brain, this is really because of eyeball rotation. And we can wirelessly transmit EOG to a laptop, and laptop can decode the signal and control a drone. So this is a video showing that the drone is flying according to the subject's eyesight. If he looks right, the drone flies right. If he looks up, the drone flies up. So this is a demonstration of an imperceptible human-robot interface, as you can see. And because graphene is so invisible, we can also put it on other prominent body parts like the palm. The palm is known to be the best location for something called electrodermal activity, EDA, or galvanic skin response, GSR. That is basically the conductance of the skin changed by the feeling of the sweat glands. We know when we are nervous, our palm becomes wet. And even if the sweat doesn't reach the surface of the skin, just by feeling the sweat glands, there is going to be change in skin conductance. And this kind of physics signal or high frequency signal is going to indicate the mental stress level of our body. And skin has the highest density of occurring sweat glands controlled by sympathetic nerves. And when we are nervous, our skin, our palm sweats. That is something we can hardly control consciously. So this is a very good indicator of mental stress, and it's used in like lie detectors and things like that. So according to a report, a lot of people report stress that affect their physical health, but there are physical versus mental stress. And studies shown that only mental stress is going to induce an increase of EDA events. Physical stress, on the other hand, does not really do that. Therefore, again, EDA is a very good indicator of mental stress. So we have a graphene serpentine connected to a gold serpentine on the palm, and we are benchmarking against the gel electrodes. The small screen is from our graphene tattoo. The big screen is from conventional gel electrodes. Although graphene is so thin and so fragile, through this so-called heterogeneous serpentine ribbon connector, we are able to do very ambulatory mobile sensing of EDA sensors using graphene on the palm. And the gel electrodes, as you can see, are very, very visible and stigmatizing, but the graphene tattoo is almost imperceptible. And they can do a lot of workout, sleep, driving, those kind of daily activities. And we reliably record 24 hours straight EDA signals from the palm using the tattoos. And here is a controlled lab study by showing subjects with effective pictures and videos. We can induce those so-called EDA events. And compared with those red curve, which is the stiff, thick gel electrodes, we can see that actually the physics signals are very, very comparable. And if we count the number of events, those are also very comparable across a cohort of 5 subjects, validating the efficacy of graphene eta 2 for EDA sensing. But speaking of not just mental stress, but mental brain activity and cognitive functions, another very significant non-invasive sensing modality directly on the scalp is called EEG. And it is measuring the cortical pyramidal neuron postsynaptic potentials, which are actually averaged and filtered by the scalp, reaching the surface of the scalp skin. And for different brain regions, we know that roughly speaking, they are responsible for different functions, like the frontal lobe is more for decision making, reasoning, and the parietal lobe on the top of our head is more for calculation, reading, writing, and the back of the head, occipital lobe is vision, and temporal lobe is memory, and so on. So therefore, if we want to capture the comprehensive cognitive activities, we have to use this kind of so-called shower cap with the gel electrodes to cover the whole scalp. And there is an international 1020 system where you can see that the separations are 10%, 20% placement of those electrodes, such that we can do a standardized montage of those electrodes. So EEG has a lot of use, not just for clinical neurological disorders and cognitive and neuroscience functions. Nowadays, it's also widely used for brain-computer and brain-machine interfaces. And here we are featuring Sheldon because everyone wants to decode Sheldon's smart brain, right? So first, we thought, okay, we can still use patch like ETA 2s on hairless skin, for example, on the forehead and across the eyes. We're measuring vertical and horizontal eye movement. Like I mentioned, those EOG could be 1 millivolt level, but the EEG are on the order of 1 to 100 microvolt. So EOG could be a big contamination for facial or prefrontal lobe EEG. So as a result, we measure EOG as a noise cancellation for EEG. On the other hand, EOG also indicates eye movement, including blinking and saccade. So those could also be useful for like a mental performance indication. And here we have a customized adhesive PETA PSS composite coating on top of a really dirt cheap graphite polyurethane sheet. And by applying this coating, even though it's dry, like maybe with a little bit of water, we are able to drive down the contact impedance even below the liquid gel electrode. And that is because PDOT is both ionically and electrically conductive. And we have engineered a wireless 4-channel EEG and 2-channel EOG flexible circuit board pairs with this blue sheath-covered battery so that we can do completely wireless mobile EEG and EOG. And here we carried out a so-called N-back test, which is a strong indicator of working memory. And the higher the N, the higher the workload. Using our measured EEG and EOG, we're able to use a very basic random forest machine learning algorithm to decode the mental workload. Not perfectly, but at least it's an objective measurement rather than the self-report NASA NLX kind of questionnaire. We are happy about this work, but we didn't expect that it caught a lot of media attention. Maybe because everyone really felt mentally overloaded and strained every day in this fast-paced modern life. But speaking of those hairy scalp, we know that hairs are going to be a big problem for patch like ETA 2s, and conventionally nurses have to come in with rulers and pencils to measure and mark those different locations and put on liquid gel and clip on the cables one by one. Those dry electrodes comb finger-like are quite stiff and uncomfortable for long-term wear. This is Professor John Rogers' e-tattoo that is applicable if we're willing to shave. So what we would like to pioneer is this kind of liquid conductive ink that can be, for example, inkjet printed onto the hairy skin surface. And after a few minutes after printing, the ink can self-dry or even heated dry such that they form this 10, 20, 30 micron thin kind of dry conductive thin film on a hairy skin surface. And to develop the ink, we again use the PEDOT-PSS given its electrical and ionic conductivity. However, we know that PEDOT by itself is quite stiff and brittle, and we therefore added a DMSO to really enhance the electrical conductivity. That is a well-known method. We can add glycerol as a plasticizer to enhance the stretchability and reduce the stiffness. We can add salt to actually improve the ionic conductivity, and therefore they are ideal for electrodes. And using DMSO enhanced electrical conductivity, we are able to use them as interconnects. So those are different types of inks we formulated with the help of Professor Ximing He at UCLA. So this is wet ink, this is dried ink, and this is to show the conformability under SEM as a cross-sectional view. And because of those added salt, we are able to see ultra-low contact impedance on the skin, even lower than gel electrodes. And here we summarized the reason why this kind of ink-based PEDOT-PSS electrode can achieve ultra-low contact impedance even without doing abrasion. That is because of both mechanical conformability as well as those ionic and electrical conductivity. So here is a highly speeded up video showing the non-contact inkjet printing of those electrodes. Those are salt-rich ink. And this is a real-time video showing after the electrodes are dried. Here we are printing those high conductivity DMSO-rich PEDOT-PSS ink that has high conductivity but also high contact impedance with the skin. So only the electrodes can pick up the signal, but those interconnects are just conductive. They are not able to pick up any signal due to the high contact impedance with the skin. And here is a validation. Again, we have to connect those printed tattoos with those data acquisition box. Here we're using brain vision in both cases. And we can compare the EEG measured, but after 6 hours, we can see gel dries completely, but the printed tattoo, because they are already self-dried, right? So after 6 hours, not much difference. And we can measure things like motor imagery and error-related potential. Those are very popular BCI signals used in a lot of like robot control and human-machine interface and so on. So they are also very easy to remove if you just apply shampoo to do a brain like a hair wash, or you just use even alcohol wipe to use mechanical force as well as alcohol to remove them. So in addition to like a brain mental stress and mental workload, we are also able to monitor a lot of cardiovascular function, both for health and for performance. So here is a wireless e-tattoo measuring simultaneously ECG and SCG. SCG is a mechanical vibration due to heartbeat, but on the surface of the chest. You can use your finger, right, to feel your heartbeat. So this is 3 channels of XYZ chest vibration plus 1 channel of ECG. You can see during movement, ECG is very, very stable, but SCG is measuring the vibration, so it's doing its job. But the real SCG signal is embedded in this vibration, and that can be actually retrieved using signal processing. So here we are showing this ultra low power and low weight chest conformable wireless dual mode e-tattoo that can give you, of course, very accurate heart rate. This is ECG based heart rate compared with smartwatch that is PPG based heart rate. We can infer a stroke volume as well as blood pressure if we have done enough training and a machine learning process to assess those non-directly measurable biometrics. And just very quickly, in addition to cardiovascular, here is some muscular performance. We know that EMG is usually under a lot of motion, but here with the hardware engineering, we can highly stabilize the EMG even during this kind of full out kind of cycling and across multiple days. There's no change of the signal to noise ratio, and we can use this kind of multi-day wearable muscle eta2 to indicate muscle fatigue. As you can see, like very clean median and mean frequency decay and the red IMS kind of roughness increase over days. And finally, we know that body hydration also affects our mental, cardiovascular, and muscular performance, actually. And currently, it is possible to measure a sweat rate. But if we want to know the whole body hydration, we are using this kind of a cross-brachium bioimpedance, tetrapolar bioimpedance measurement to make sure the current has to flow through the muscles, not just the skin. And the white curve is our 24-hour ambulatory arm impedance sensor versus this yellow curve, which is the body weight change. Especially during this 3-hour dehydration experiment where we gave the subjects diuretics to make them urinate without having food or drink, their body weight loss is closely representing the body hydration and the bioimpedance, just the segmental local bioimpedance across the arm is able to track that closely. And from the impedance and inductance, we can also have the so-called bioimpedance vectoral analysis to show that during dehydration, the vector goes toward the upper right. That is a strong indicator of dehydration as well. So as a summary, we hope to build an eta2 body sensor network ultimately for decoding the human body. And currently we are showing you those individual sensors, but in the future, we really hope that we can fuse their data and their capability to indicate things like mental plus physical fatigue and a lot of other things like stress and pain. So as an acknowledgement, let me thank all of our collaborators in different domains, especially Professor He helped us started all those PWPSS work, and Professor Jose Mian helped us with a lot of those BCI work. And with that, let me thank my wonderful group at UT Austin and all of our sponsors over the years supporting our work. And of course, thank everyone very much for your attention, especially those in almost midnight time in China. Thank you.
Thank you very much, Professor Liu. That was a really interesting talk. Just a reminder, everyone, to pop your questions in the Q&A section on the chat. I'll start off with a question of my own, if that's all right. I wondered, is it possible to synchronize data from lots of different e-tattoos?
Yeah, that's always not easy. So if individually they are wireless, there are a few ways that we can synchronize the data. First is just a hardware global signal synchronization, like we can have a shared movement, like an artifact will show up in those individual sensors, and we can manually align the signals. Or currently we are using actually a app on the desktop called Lab Streaming Live. We are able to have a shared clock for all of those signals coming into the same central device. There are many other ways people are exploring, like the body capacitive link and other things that can help do data synchronization at a low power.
Great, thank you. And we've got lots of questions coming in. So we have one question from Guyun Chung. When applied in daily life, can the e-tattoo remain intact for several days when you're washing your hands or taking a shower? Is there any research that's being done to kind of make it waterproof in the future?
Yes, that's a great question. So, for example, this kind of surface EMG tattoo has been worn. Actually, we show 6 days. So, subjects were released back home, taking shower, actually doing workouts, and so on. So, here is 3M Technum tape that is waterproof but vapor permeable. But you can see, like after a few days, the edges start to detach. So, we can, of course, engineer like more breathable and like a more adhesive, but still easy to remove interfaces with the skin.
Great, thank you. I think we've got time for one more question. Jinghan Lee asks, inkjet printing works for short hair, but if you have long hair, I guess that would be more difficult. Are you currently exploring any potential solutions there?
That's a very good question. Yes, indeed. It only works for bold or buzz cut. We actually have to really motivate our subjects, participants to shave their hair for science and the technology. So currently, what we're exploring is also liquid ink that can be a little bit more viscous, such that we can use a brush to dip and manually paint using a painting brush. Of course, that's a manual process. We have to part the hair, expose the scalp, and paint. And then that also takes a longer time to dry because the painted ones are thicker than the printed ones. But yes, if we have long hairs, it will have to be some other technology. But the painting could be a temporary solution, especially for our collaborators who don't have the 3D printer. The painting is something they said they can accept.
Great, thank you. Thank you very much again, Professor Liu. That very interesting talk, and thanks all for all the questions. Just to note, we will be sending a follow-up email after the event to all attendees, so we'll see if we can answer some of those additional questions within that. So yeah,
Sure.
thank you once again, Professor Liu.
Thank you.
Okay, so before we move on to Professor Rogers' talk, I'd just like to take a brief minute to flag up the interdisciplinary journals in the RSC's portfolio, all of which would be very welcoming of work on wearable sensing. So our flagship journal, Chemical Science, is published Diamond Open Access. So all the articles are free to read and free to publish for authors. So do go and check out some of those. And then we have our reviews journal, ChemSoc Rev, and ChemCom, which publishes urgent communications. And then finally, RC Advances, which is our community-led open access general chemistry journal. So do use the QR code to explore all of those. Again, we have our general journals, but we also have topic-specific journals, and one of these is Lab on Chip, led by Editor-in-Chief Aaron Wheeler, and it's actually currently open for submissions for a theme collection on microfluidics for wearable and implantable technologies, which might be relevant to some of you working in that field today. So please do consider submitting your latest research to that collection before the middle of June. So you've got a few weeks still to get those in. And you can use the QR code on the screen to find out more about the collection and discuss your submission with the editorial office. Okay, so with that, it's my pleasure to now introduce our next speaker, Professor John Rogers. Professor Rogers is at Northwestern University as the Simpson Query Professor, where he's also Director of the Institute for Bioelectronics. His current research focuses on soft materials for conformal electronics, nanophotonic structures, microfluidic devices, and micro-electromechanical systems, all lately with an emphasis on bio-inspired and bio-integrated technologies. So yeah, we're looking forward today to his talk on advances in skin-interfaced wearable sensors. So yeah, Professor Rogers, take it away.
Okay, great. Thanks, Geraldine, for that introduction and for inviting me to participate in this webinar. It's a real honor to be able to share the stage, so to speak, with Nanshu, and it's a really beautiful talk. I enjoyed her presentation. And the other good thing is it kind of sets the stage for what I'd like to share in my talk. And specifically, I'll focus on some very recent advances in our group around this concept of skin interface wearable sensors, two classes of sensors that we've just published in the last month or so. But I'll begin with kind of a motivation, a perspective, a context around this area of technology where chemistry can play a role, and kind of conclude with some outstanding challenges where I think people with a sort of chemistry expertise will be able to contribute to this exciting field. So my own expertise is in materials science and engineering, but we like to think at the system level. And so a lot of what we end up working on is highly interdisciplinary across various areas of science and engineering, but with a close sort of interface and set of collaborators in the clinical medical community as well. And I have close ties to our departments of neurological surgery, dermatology, and our focus lately is on maternal, fetal, neonatal health, as you'll see as I move through my presentation. So I guess this sort of area of wearable sensor technologies falls within a broader category of research that sort of focuses on this notion of bioelectronics. And by that, we mean classes of electronic devices that can in principle support the sophistication and function provided by silicon integrated circuit technology, but formulated out of materials and geometries and with mechanical properties that allow that function to be integrated intimately on, around, or throughout soft living tissues, with a focus ultimately on utility and human health care and patient care in general, but also thinking about the resulting technologies as enabling new research paradigms around small animal model studies of topics in neuroscience, for example. So that's sort of sets the stage for a whole set of activities in materials science and chemistry to develop these classes of biocompatible electronic systems. And you have to think about the active materials, the encapsulation layers, the substrate materials, and so on, that have to be biocompatible at a molecular level, but in many cases also require sort of consideration of mechanical and geometrical features. And Nancy really highlighted, I think, sort of a breakthrough advance, conceptual advance that she was deeply involved in as a first author on this paper back in 2011, where we were able to introduce the idea of skin-like or epidermal electronics. And Nanchu and others refer to this class of technologies in e-tattoo, also another way to kind of think about it, where all of the physical properties of these electronic devices are really precisely matched to those of the epidermis itself. And so you can think about them as a functional second skin that laminates directly on the surface of the natural skin to establish an intimate interface that allows for the use of the skin as a window for measuring underlying physiological processes, as Nanshu so clearly outlined in her presentation. And so these classes of devices really represent a blend of both hard and soft materials, organic and inorganic materials in hybrid collections that afford these biocompatible sets of physical properties, but at the same time offer the kinds of performance characteristics that really can match those associated with conventional wafer-based electronic circuit chips. So that's the idea. The question then is, what is it good for? What would you use that kind of technology for, and what kind of sensors might be most powerful to deploy, on human subjects using that sort of unusual form factor? And I think of the many possibilities that one could consider, we really tended to focus, at least initially, on early life health challenges. So specifically, as I mentioned before, maternal, fetal, neonatal, and pediatric health. These are vulnerable patients, especially in the developing world. There's a lot of mortality associated with childbirth, and early childhood health challenges tend to create problems that persist throughout the entire life of the individual. And so developing new technologies that could address those classes of patients might be an interesting area to sort of focus one's application-oriented research activities. And so specifically, we've developed classes of devices in this epidermal format that operate in a wireless fashion to recapitulate all the vital signs monitoring that's done in pediatric intensive care units, neonatal intensive care units, eliminating the burdens associated with the wired interfaces that are typically used to connect hardwired sensors that are taped to the surface of the skin to external boxes of data acquisition electronics. And this is an example of participant in a study that we engaged in with clinicians at Princess Women's Hospital here in the Chicago area to monitor vital signs in pediatric patients. And so you can see it's two devices that recapitulate all the vital signs that are tracked, even in a level 4 NICU and PICU facility. The device on the chest is capturing cardiopulmonary signatures of health through ECG recording and surface temperature measurement. And then the device on the foot, you can see in this image, is a 2-color photoplasmography data collection unit that allows for determination of blood oxygenation. And both of these devices are operating in a continuous wireless streaming fashion, battery-free operation using wireless power transfer from, in this case, a transmission antenna mounted in the base of the chair. So this is kind of what it looks like. We got started and published our first paper in that space in 2019, really started a focused effort in that area of clinical care in 2016. And since then, we've really been focused on translation. How do you get technologies like that out of the lab into the real world through FDA regulatory process and thinking about manufacturing and scale and costs and the rest of it. And I won't go into the details here, but I think we're well on our way to establishing this technology as foundational capability for the future of human healthcare in clinical settings. And this is being done through a spin-out company from our group called Cybal Health. And some of the parameters associated with the current status of the technology are illustrated here. So I can't take any credit for that. It's a broader team, about 130 people at this point, and with worldwide deployments. Into the developed world, but also lower and middle income countries as well, with philanthropic support from the Steele Foundation, the Gates Foundation, the Save the Children organization. So we focus on neonatal and pediatric patients initially, but as I mentioned, you can think about maternal health and fetal health as well, specifically during the intrapartum period. So we extended the pair of sort of wireless sensors that I described before to monitor the health of the mother, but then added a third wirelessly synchronized device to mount on the stomach of the expecting mother to track fetal heart rate and uterine contractions. And so you can do that, and it works extremely well, really matching the sort of data fidelity and quality and accuracy that's obtained with conventional wired-based systems, but in a much more cost-effective manner that also reduces a lot of the hardware burden on the mothers during that birth process. And so the relevance then extends to resource-constrained areas of the globe. And as I mentioned before, we have philanthropic support and large-scale deployments of these kinds of technologies into various countries in Africa, India, Pakistan, and a few countries in South America as well. And we kicked off a relatively large program just this time last year. And started deploying devices in January. And I was able to spend a couple of weeks with the Cybal team in Lagos, Kigali, and Nairobi just in January to begin deployment of these maternal fetal health monitoring technologies. So then the question is, what else could one do with skin interfaced wearable sensors in this broader space? And the visibility of our activities in this area led to inbound inquiry from physicians associated with our Princess Women's Hospital here in Chicago, neonatologists specifically. And they asked whether we could develop sensors that would allow one to determine how much milk is being consumed by an infant during breastfeeding. And it turns out natural breastfeeding has tremendous health benefits, not only for the infant, but for the mother as well. But there's a lot of uncertainty and stress associated with not knowing clearly how much milk a baby is consuming during breastfeeding. And so a lot of natural breastfeeding doesn't persist throughout the recommended time frame provided by the World Health Organization. And the reason is due to uncertainty. So many women prefer to use a pump so they can see exactly how much milk is being consumed out of a bottle, but you lose a lot of the benefits of that more natural breastfeeding activity. And so the question was, could you develop a sensor that would provide real-time information on milk consumption during a breastfeeding session so that a mother can see how much much milk their babies are receiving. And that turns out to be particularly challenging for premature babies because of their limited ability to suckle in a natural and an effective way during breastfeeding. So we ended up going down a number of dead ends, and in seeking to develop a sensor of that type, we had devices that were monitoring numbers of swallows associated with a baby during breastfeeding, but it turns out many swallows don't correspond to any milk volume intake, so that didn't work. We tried to measure the amount of milk reaching the stomach of the baby using various kinds of approaches. We then shifted towards technologies and sensors that would allow, in principle, the measurement of actual flow of milk through the nipple into the baby. That turned out to be sort of confounding and complicating in terms of disrupting the natural engagement of the infant with the breast. So we had to discard that approach. We started looking at optical techniques that would allow us to measure light transmission through the breast, and that turned out to be quite difficult in terms of removing effects of ambient light. So we ended up using a very simple approach, actually very similar to the impedance measurements that Nanshu described for measuring core hydration. But instead of measuring hydration of the body, we're measuring milk content in the breast using low frequency AC impedance measurements, using pairs of electrodes mounted on either side of the breast, and monitoring the impedance at frequencies that correspond to measurements that are very sensitive to liquid that fills the interstitial space in between cells within the breast, and specifically capturing the effect of transport through the milk itself. And so this turned out to be an extremely effective way to do the measurement in a way that didn't disrupt the natural breastfeeding process, because the electrodes can be mounted sufficiently far away from the point of engagement between the infant and the breast to not induce any complication, as I mentioned before. So very simple device, just two pairs of electrodes, a small wireless electronics unit that's doing data acquisition, supplying the AC current to a pair of these electrodes, and then capturing the voltage difference measured from the other two electrodes to determine the impedance, and then transferring that information wirelessly to a Bluetooth-enabled external device, a smartphone, for example, that allows for real-time graphical display to the mother during the feeding session. So you can actually just watch the baby consuming milk directly in graphical form on the smart device. And so there's a lot of modeling that went into understanding the underlying physics of this type of measurement, and actually providing sort of guidance for optimization in terms of positions of the electrodes and the sort of frequency that's used to determine the impedance. And there we collaborated with Avila Raudel Avila at Rice University. He used to be a co-advised PhD student with myself and Yanggong Huang here at Northwestern University. So he's done a fantastic job of taking MRI sections to develop realistic models of the breast and the location of the breast milk, and then using those models and finite element modeling technique to understand current spreading and the basis of this kind of impedance measurement technique for monitoring the amount of milk that's in the breast, and therefore the change in the milk volume associated with consumption by the infant. And the interesting thing here is that you might naively think that the impedance would decrease as the milk volume is extracted and the overall volume of the breast decreases. But it's actually the opposite trend, because the conductance of the milk itself is higher than that of the surrounding breast tissue. And so as you remove milk, the impedance of the breast actually goes up. And it changes by about 10% for a complete breastfeeding session. And so the measurement technique really demands a fairly high level of accuracy. You need to really be able to measure a change in impedance to an accuracy of about 1% if you want to be able to make a useful measurement of this type to allow mother to watch milk consumption in real time. So it required a fair amount of optimization around the electronics and minimizing the impedance between the electrodes and the surface of the skin of the breast. breast, but if you're careful with a lot of those sort of engineering factors, you can develop devices that offer the required level of accuracy and impedance measurement for this particular application. So you see representative data on the lower left part of this graph, and so that's normalized change in impedance in percent as a function of time while a new mother is engaged in a breast pumping exercise. And we do this to establish a calibration factor that connects impedance to milk volume. So when we're pumping, we can just measure the amount of milk that appears in the bottle, and we measure that every minute or so. And then we can establish that sort of correlation graph or calibration which establishes a linear connection between the fractional change in impedance and the milk volume that's been removed from the breast. And so once you've done that single calibration, it turns out that calibration persists over several weeks, provided that the electrode placement on the breast is consistent. You only need to do calibration once, and then you can read out milk volume consumed over a much longer period of time. And that's what's indicated in the upper left graph. So this is for a particular subject at several breast pumping sessions, so we can determine the accuracy of the measurement. And we see that the linear calibration between change in impedance and milk volume persists over time. Then we were kind of curious, is there sort of a universal calibration factor? And we did 12 different participants in these studies. And you can see that there's a rough correspondence, but there are anatomical variations associated with breast size and body type and so on. And so to get the highest accuracy, you do a calibration on a per individual basis. And so this provides, sort of a solution to an unmet clinical need that turns out to be important for new mothers. So that's one example of sort of measuring flow using skin interfaced wireless devices. We've also gotten very interested in thinking about sweat as a class of biofluid that's interesting because it can be captured non-invasively. It's also very rich from a biochemical content standpoint. And so as an alternative to blood, for example, sweat might have sort of a certain level of appeal and convenience for doing biochemical assessments of health status to complement a lot of the biophysical measurements that can be done a little bit more easily with these skin interface wearable devices. And so we got interested then in the development of skin-compatible microfluidics, or the lab-on-a-chip type technologies. And you mentioned this focus issue in the journal Lab-on-a-Chip, and we've published several of our papers in that journal. And so what we've developed is sort of an analog to skin-like electronic devices, or skin-like lab-on-a-chip devices, or lab-on-a-skin type devices. So these are soft, completely sealed microfluidic systems with microfluidic networks of channels and valves and reservoirs. They can be adhered to the surface of the skin, whereby the sweat glands themselves can serve as a pumping source to drive eccrine sweat up into these microfluidic networks through the channels and valves and into reservoirs, where we locate colorimetric chemical reagents that respond selectively through a color change to the concentration of various biochemical markers of health that we're interested in. And so these devices allow us to measure sweat loss, sweat rate through that sort of serpentine channel that runs around the perimeter of the device, but also sweat chemical content, as I mentioned in this particular case, in 4 circular reservoirs that are filled with reagents that respond to lactate, chloride, glucose, and pH, for example. So it turns out to be very simple devices, non-electronic devices that allow for digital readout through color analysis from images captured of the device using smartphone camera, for example. And so we're interested in translation in this technology as well. And we've sort of pursued, those opportunities in a separate startup, sort of moving forward in parallel to Cybele Health, as I described before, starting with a non-medical application in a partnership with Gatorade to provide information through one of these skin interface microfluidic patches, information at the customer base on the amount of sweat that they've lost and the electrolyte loss that they've suffered during an athletic competition or a workout or fitness routine to guide sort of precision supplementation or water and electrolyte intake to balance those loss channels. But we're also interested in medical applications, and there's where there are tremendous opportunities for advances in chemistry. So here's one example. We're interested in sweat creatinine and sweat urea in the context of monitoring patients for kidney disorders. And so we've developed a colorimetric enzymatic sensor for measuring the concentration of creatinine and urea in sweat. And then the question is, what does the concentration of creatinine in sweat have to do with corresponding concentrations in blood? And that becomes a question around human physiology that really can only be answered by large-scale human subject studies. So this is a topic of current work where we've enrolled about 12 kidney patients so far through collaborators that we have with the Department of Nephrology at University of Illinois, Chicago. And what you can see through these early studies is that the concentration of creatinine in sweat and urea in sweat correlate pretty nicely to corresponding concentrations in blood, foreshadowing potentially sort of very low cost, easy to use home diagnostic of kidney health. And so I think developing similar types of colorimetric chemistries for other chemical constituents in sweat could be a very valuable area of chemistry research into the future. But for the last 2 minutes, let me describe sort of a new technology in this broader space of transepidermal flux. And we're interested in sweat, certainly something that one can focus on. There's a lot of value in that line of research. But in some cases, you might be more interested not in liquid transepidermal flux, but in gaseous flux. Your skin is always breathing, not in a conventional cyclical sort of respiratory sense, but there's all kinds of chemistries coming up naturally from underlying tissues through the surface of the skin. And could one develop a technology for sort of capturing and quantitating that gaseous flux and determining volatile organic compounds, for example, that might be emerging from an infected wound site, or water vapor that's dominating water loss in neonates in the form of transepidermal water loss, or carbon dioxide, transcutaneous CO2, also of clinical interest. And so there we've developed a slightly different device, not microfluidic. It's a device that forms a sealed chamber at the surface of the skin. And instead of having sensors in direct contact with the skin, we have sensors as sensor suites sort of floating within that chamber. And in addition to that chamber, we have a programmable valve that allows us to close that chamber to the ambient or open it to the ambient. And so when that valve closes, we can measure the time dynamic change in concentrations of various gaseous species that emerge into that microclimate as a way to determine quantitatively the flux of those species up through the surface of the skin. And so this is sort of a exploded view cross-sectional illustration of how the device is designed, that floating sensor suite within that chamber, that microclimate, and then a bistable magnetically activated valve that allows us to open and close that chamber to the surrounding environment. And so you end up with transient measurements. You can capture the concentration of various gaseous species as a function of time. When you close that valve, you see that sharp increase. And from the initial slope associated with that increase, you can determine a quantitative value of flux. You can measure outflux, but you can also measure influx. So exogenous chemical toxins, for example, in an environment, you can measure the rate at which they're entering the body through the skin using the same kind of device. And so we're quite, excited about this new platform for measuring skin flux. It's a wearable device, very similar to the other devices I've described to you, and you're capturing this flux value sort of in a episodic fashion. Every time you open and close the valve, you get a flux measurement. And so you can measure changes in transepidermal water loss, for example, over sleep night. That's what's shown in the upper graph here. But maybe even more importantly, you sort of monitor the dynamics of various wound healing cascades that occur in both healthy and diabetic patients, and that's an area of focus for us currently. So I'll just go ahead and conclude with 2 devices I wanted to share with the group here today. This platform for determining molecular flux, gaseous flux from the surface of the skin. and a device that's designed to measure continuous uptake of milk during breastfeeding. But I think all of this opens up really interesting opportunities for the research in the chemistry community, and I sort of list some of those opportunities here, and I've sort of tried to outline them through the course of my presentation. But chemically specific sensors for VOCs and also for chemical species in eccrine sweat. Dry skin adhesives are always a challenge. Some advances in materials chemistry could be very valuable there. Soft electrodes, dielectric impedance spectroscopy for milk quality is something we're very interested in. And something more in maybe biological chemistry is understanding bacterial metabolism and growth and VOCs that are emitted from bacterial colonies that can develop at wound sites. So many different opportunities for the chemistry community that I think are quite exciting. So I'll just conclude with a list of senior collaborators. I've mentioned many of these folks through the course of this presentation. I won't go through each one, but they're listed here. And conclude by acknowledging the really amazing work of the students and postdocs in the group. So thank you very much for your attention.
Thanks very much, Professor Rogers. That was, really fascinating. Thank you. So again, feel free to pop your questions into the Q&A panel, and I'll start with one of my own if that's all right again. For the skin flux sensor, what organic compounds are you really looking for monitoring wound infections?
Yeah, there's a whole series of them. It really depends on the type of bacteria, acetone. There are various kinds of alcohols that come off of a wound site that's become infected. And so the goal is to develop gas sensors that offer very high levels of sensitivity, so you could pick up very early signs of an infection before it becomes a problem, so that you can deliver antibiotics or other kinds of therapies to treat that infection before it becomes problematic. Ultimately, you would like chemically selective gas sensors, because the chemistry of the volatile organic compounds provides really great clues into the type of bacteria that's beginning to develop at the wound site. So there's a whole list of the specific chemistries that one can find in the literature, and a lot of them are alcohol type chemical species.
Okay, great, thank you.
Mhm. Mhm.
We have another question. For the breast milk sensor, is there any way of determining a metric on the quality of the milk, or is it?
Yeah. Yeah, we're hopeful that's possible. That has been a request from our clinical collaborators to determine a metric of quality, fat content, for example. So we have done dielectric impedance spectroscopic measurements of different samples of milk, fat-free, 1%, 2%, whole milk, and you can see differences there. So just benchtop studies. It will require a frequency sweep on the kinds of impedance measurements that we're doing now. And we're hopeful that you'll be able to determine both volume and quality from a single measurement system. But we haven't proven that out yet. It looks hopeful, but it's a question of accuracy. And the impedance is a combined quantity that depends not only on the dielectric properties of the milk itself, but the volume, and sort of coupled together. And you kind of have to try to disentangle those two parameters.
Yeah, interesting. Okay, great. In the interest of time, we might have to stop there. But yeah, really, thank you again, Professor Rogers. That was a really interesting talk. And so that brings us to the end of our webinar. If you'd like to discuss any of the research that you've seen presented today, the speakers have kindly shared their contact details, so do get in touch. And of course, get in touch with us at the RSC if you would like to have any questions about the RSC. A big thanks to everyone really for taking the time to join us today, and a special thanks to both of our speakers. Thank you, Professor Liu and Professor Rogers. Really excellent talks and a great Q&A session. So yeah, thank you for that. And we hope to see you all at a future RSC desktop seminar. You can find recordings of all of our previous webinars and information about upcoming sessions at the QR code on the screen. And finally, just a very brief call to action from me. If you're interested in working with us to improve the tools and services that the RSC offers, then do sign up via this form to stay informed about future opportunities to test new features and share your feedback. And I'll end it there. So thank you very much again. We hope to see you soon. And thank you to our speakers.
Okay, thank
Have a
you.
good day.
Okay,
Thanks.
bye.
Bye.
Bye.